Okay, so we are ready to go now. First slide, obviously, about myself. You can, for office hours and other reasons, if you want to meet me, you know where to find me. You can also use this QR code to learn more about some of my research work and what I do in general. That way, you'll be able to relate why I care about this advanced memory topic as opposed to other things. Okay, and by the way, I go by Ahmed. You can call me Ahmed. Just wanted to point that out. Now, that brings us to the very first technical slide of this lecture. It's more like a breakdown of different components of digital system. We often use the term that we are living in the digital era. Everything is digital. But what does that truly mean? Basically, the digital fabric is made out of computing systems that help us process information in a digital format. And you obviously know by digital, I mean binary, ones and zeros. We deal with ones and zeros. We have memory that helps us store information. We have sensor that helps us convert any kind of information to digital format. For example, a temperature sensor converts temperature information into streams of ones and zeros. A heat, like light sensor, smoke detector, whatever, like the magnetic field sensor, they convert all sorts of analog-ish inputs to digital format. These are more recent ones. We'll probably not have time to talk about them here, but this course will cover towards the end of it, computing memory. We have one lecture in computing memory. The reason is there is memory involved here. So I'll try to cover that. This is the most advanced form of memory utility. People are doing it right now. Okay, and computing sensor is even more advanced, like it's up and coming right now. I'm not going to dive into any of them. I just want to show how important memory is in the overall dynamics. It's almost at least 1/3, if not more, right? In terms of defining the overall digital universe. But now tell me, have any of you taken any course where you learned about designing logic, like CMOS logic? Yes, several of you. Which course? Could you point some course numbers to me? 433, 335 to some extent, maybe 250, like digital logic design, right? DLD. So it's all about logic, and they all fall under what? Computing, don't you think? Doesn't matter whether it's a Boolean logic system, whether it's a CMOS-based NAND gate, NOR gate design, or 433 folks must have gone through non-CMOS categories as well. I don't know. Doesn't matter. It's all about logic. Turns out, for the longest time ever, for decades, all educational activities primarily focused on teaching people how to design computing systems. Because at some point, that was the bottleneck. We needed more computing power. And memory was like an afterthought. Okay, we'll figure it out later on. That doesn't mean memory is a recent invention. I'll show you that. They have been there. They have been pretty benign. People have been just using the same thing over and over again. So there was not too much excitement. Oftentimes, even in 433, I remember, I have one lecture on memory design. So that was about it. Okay, memory, some circuits, there you go, done. But just imagine how critical it should be, ideally, given the 1/3 nature of memories. Even more so, if you think about how critical this thing is in the overall dynamics. Let me show you. This is a simplified picture of how processor memory are connected in a computing system. It could be in your iPhone, it could be in your laptops, it could be any other, like a supercomputer even. The core skeleton remains the same. You have a storage system. Obviously, I'm using the term memory here, but essentially it's a storage system. And you have a processor that just processes information. You have to connect these two because the processor needs to fetch the information from somewhere before processing it. So it has to be stored somewhere, okay? First. Second, after the processor processes an information, it will have to store it back somewhere else. And in between computation, maybe like, for example, you're trying to add A, B, and C. Just think about a very, rudimentary example. After you add A and B, you have to store the result somewhere and then bring C and add that with the result. So in between computation, you also need to use storage, right? As simple as that. So the processor has to communicate with the memory every once in a while through data bus. And there are other peripheral circuits, as you see, obviously. So these peripheral circuits and data bus allow the processor and memory to communicate with each other, but they still have to communicate. So looks like any computing system, to be honest, there couldn't be any computing system without memory. Just imagine that. So it's more than 30%. It's almost half of a digital universe. In fact, in most sensors, you need storage as well. Okay, so I don't want to get to that degree of detail, but you get the point. I also want to highlight the criticality of memory devices and how important it is to make every one of them work. And I use this example quite often. You must have seen that before. Digital universe deals with binary digits, ones and zeros. Okay, and this example shows you that for every letter in English alphabet, we have an ASCII code. An ASCII code is nothing but a stream of binary numbers. Okay, so the difference between C and B is basically in one digit, as you see, just one digit. And you have to store that digit somewhere. If for some reason you accidentally misread a digit from 0 to 1, or misprogram your memory, and instead of 0, you have 1, you have only two options. It could either be 0 or 1, right? So if you somehow have a mistake, then cat could become bad so easily. And this is a benign example. Okay, it's not a very big deal, but just think about numbers changing. Your bank account number could change. Your total money that you have in your bank could change from 1 to 0, as you can imagine, depending on where that 1 is, whether it's the most significant or the least significant. You could have a far-reaching consequence, right? And there are many other aspects. Just want to highlight how critical it is to store and read every bit of information with utmost care. So every bit of information has to be stored in every bit of memory device. And we'll talk about these memory devices gradually. Now, this is more like a classification, obviously not a holistic list. This is an example of how vast the options are. Memories could be divided into two major categories: volatile memories and non-volatile memories. What do I mean by volatile? Volatile memories mean you have to keep them powered up all the time. The moment you turn off power, they lose all the information. Okay, so as long as you have power on, they will remember whatever is being stored. But the moment you remove power, there is nothing stored there. Now imagine your portable flash drive, right? The moment you plug it in, it is powered up. But when you take it out, it loses power, but it doesn't lose the data that was like all those movies and audio files, that the PDF that you have inside, they remain there. That means it has to be non-volatile. Like even if it loses power, it will still have the information stored. So that falls under the category of non-volatile memory. So you might be wondering, okay, why would we even use volatile memories? Because they're fast. Okay, remember, volatile memories are the most widely used memories. They're everywhere. Every one of you have some sort of volatile memory on it. If you have a cell phone, if you have a laptop, every computing device requires a volatile memory. That's how ubiquitous it is. Okay, so there is no getting away from volatile memory. Your options are also very limited. You don't have too much options for volatile memories. And we'll talk about both of them with utmost importance, SRAM and DRAM, and we'll talk about them in the course. And by the way, there will be topics of your midterm exam, as you can see, because you have to know them, no alternative. Others, yeah, may not be part of midterm exam, may not be part of your final project even. But they will be part of the lecture. You should learn about them. And if you choose to do so, you could forget them after the course. Okay, anyways, for non-volatile memory, there are many options. Ferroelectric RAM, phase change memory, magnetic RAM, spin transfer torque RAM. How many of you have learned or heard about some of this term in the past? Some of you. Have you heard about all of these terms? No? Everyone? Okay. So have you taken any course anywhere that taught you anything about any of these topics? If you have taken 433, then you may have heard about SRAM and DRAM. But very basic, right? So that was it for the longest time. People knew about SRAM and DRAM, but that's not even half of the picture. right? If everything were SRAM and DRAM, there would be no storage available anywhere, right? Everything will have to be powered up. So just think about that for a second. So non-volatile memory was typically overlooked for the longest time, but they are probably the busiest category. People are looking for new non-volatile options moving forward. And don't worry about this. This is taken from a research article. That's why it has more information than you need. We will get back to this footprint, memory footprint, towards like the middle part of the course. Okay, I want to show you how critical certain memories are. Okay? There is another way to classify memory. This is taken from a different source. Read-write memory and read-only memory. There are some memories that you can only read. You cannot reprogram. Okay? They are rare, but they are used. For example, mass programmable memories, right? Programmable ROM, not RAM, not random access memory. There are memories that you can read and write. SRAM and DRAM obviously are among them, but there are also other non-random access memory. So what do I mean by random access and non-random access? Random access means you could read out any data from any position at any time, right? You don't have to maintain any specific sequence. But non-random means, oh, so you have to read in a chain. First read this and the other one and the other one and the other one. If you need to read something in the middle, you have to go through the chain to get to that one. Obviously, as you see, that's not the most ideal case for most memories. If you have random access memory, we would obviously prefer to use it. That's why most effort in memory design nowadays is going towards designing better random access memory. Okay, don't worry about this laundry list. I just wanted to have it there, and you don't obviously have to memorize anything. But with all of that, I want to show you the memory IC market in 2021. I could only manage to get the data for 2021. Notice flash memory and DRAM almost takes up, I don't know, more than 90% of the market share. That's all you should care about. The others, EPROM, blah, 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 it's just 1% of the market. So you can possibly just ignore it for now, safely ignore it. But DRAM, that's how critical DRAM is. That's how critical flash memory is. Are you still with me? Okay. So that's why we will, pay a lot of interest and attention to learning about flash memory and DRAM in the course. And that's the reason why I had to pick and choose certain memories and ignore some others. Okay. Now, there is a timeline. I love history. I think it adds perspective to our understanding and see how people thought about an idea. It didn't just came out, nothing comes out of nowhere. There is a process that you have to go through. So just wanted to highlight that. Obviously, I'm not going to go through the paragraphs that's written there. They're fun to read. If you want, you can read at home. Just want to highlight that making memory started before 1950s. Okay. And the size was enormous. I want to show you some of them. Like this is a memory device. Can you imagine storing information in a huge cylindrical structure? And you could only store a few bytes. And I'm gonna, fast forward through all of this. You can read them at home. I want to highlight one or few. Maybe this one. This is a very famous memory system because that was used for Apollo mission that took us to the moon. Okay, the storage capability of this guy was a kilobyte, just 1 kilobyte. And this was known as rope memory because that's what it looks like, don't you think? They used to use copper ropes out of copper. And depending on how you wind the rope, it could represent 1 or 0. And by the way, that brings an interesting aspect of memory design in general. You just have to look for physical systems that has 2 stable states. Why is that? Because you need to represent 1 and 0. Now, if I just casually think about what could be used to store information, the first thing that comes to my mind is a capacitor. If I charge up a capacitor, it could represent 1. If I discharge a capacitor, it could represent 0. Interestingly, if I can think about it, anyone can think about it. And that's what DRAMs are made of. Dynamic RAM. DRAMs use capacitor to store information. Okay. What else could be used? Think about magnetic domain. If you have a specific north-south direction, that could represent 1. If you flip the north-south direction, that could represent 0. So you could use a magnet, and depending on how the magnet is flipped, you could represent 1 or 0. Okay. Think about more advanced form of memory. Okay. Think about DNA. Human DNA is double helical, right? There are two, you know that, right? Or okay. So DNA double helix structures, like two ribbons, getting around each other, and you have ladder-like structures in between that connects the two ribbons, right? And they're made of adenine, thymine, cytosine, guanine, AT and CG. So either AT or CG. So if you have an AT layer, that could represent 1. If you have a CG layer, that could represent 0. You see that? And it's not science fiction. People are doing it, by the way. There are startups that are using DNA to store information. There are some reasons why that's necessary and could be used. So it will definitely sound like science fiction, but it's not. There are so many other options. Think of, I don't know if you have heard about ferroelectric materials. Ferroelectric materials could be programmed into having positive polarization or negative polarization by applying certain voltages. If it has positive polarization, it could represent 1, negative 0. There you go, another example. Electron spin, depending, spintronic memory is a very different class of memory where depending on the spin of the electron inside a certain material, you could represent 1 or 0. How, there are more advanced formats. Again, I don't want to completely exhaust the list because we'll talk about some of them. We'll talk about spintronic memory in today's in this course. We'll talk about phase change memory. That's another example. How many of you know about amorphous and crystalline material? A material that has specific, really nice, well-structured crystal structure is a crystalline material, like sodium chloride, for example, right? You can nicely draw a structure for sodium chloride. There are many other materials who do not have a well-defined structure. They're called amorphous. Okay. There are some materials whom you could convert from being crystalline to amorphous. Like literally, you do something to the material, it becomes amorphous. You do something else, it becomes crystalline. So when it is crystalline, the crystallinity could represent 1, amorphous structure could represent 0. You see? All right. So there are many opportunities, many options to represent logic 1 and 0 in a physical format. And people often use the term information is physical, meaning it's not just virtual numbers flying around everywhere. When you upload a PDF file on OneDrive, say, you feel like everything is software. No, that PDF file will have millions of ones and zeros. Just imagine this for a second. Just for a second. Millions of ones and zeros. When you upload it on over OneDrive, Microsoft will have to have some sort of hardware in place. Maybe they're made of capacitors, like DRAM, say. I'm just making it up. And how many of those capacitors will you need to store a million bit? Exactly a million capacitor. Every capacitor could just represent 1 bit. So the more information you're storing, more physical entities you will need to store those information. Does that make sense? So that's why information is physical. So it's not really virtual. It's there. There is a physical presence of every bit of information that we create, which we often overlook. We think, oh, everything is software. Software has a hardware backbone. Okay. All right. So moving forward, I don't want to go through this list. Please read it at home. I hope it will be fun. Just want to show you the evolution. It didn't, just take flight overnight. Maybe this is one of the exciting ones that I'll, dig deeper later on. I want to highlight this 1973 discovery. DRAM, dynamic random access memory, was invented in Japan in 1973. And to this day, we are using DRAM. You see why there were no courses about memory before? Because people just kept using the same thing over and over again. Nobody, needed to completely break away from the shackle. Even today, we are using DRAM. Like almost 50 years. I don't know, right? Almost 50 years. Okay, 50 years old technology. Move forward even further. CD-ROM, you must have, I don't know if you ever used one of this, but there's old story now. This is one other thing that I want to show you. Flash memory. That was discovered in 1980s. And to this day, it's again almost 50 years, like 40 plus years. that we're using it. And if I could just go back a little bit, see, flash memory and DRAM, even in 2021, they make up over 90% of the market. Like 50 years old technology, right? There is a saying, I don't know if you've heard this before, necessity is the mother of invention, right? If it's not necessary, nobody will invent. But now that's what brings me to the why now question. Why should we care now? Because now we are at a stage that this will no longer save us. We'll have to look for completely new storage solutions. Like we're now at a breaking point. I'll show you some examples as to why that is the case. So let's move forward. Okay, let's focus here. 1971, Intel introduced a memory storage device with 1 kilobit storage. You cannot even store a selfie. I mean, forget about selfie. You cannot even store probably a good text file with an emoji with 1 kilobyte, right? I don't know. DDR5 RAM that the same company made in 2021 had 32 gigabytes of storage. And RAMs are not even known for storing information. They're mostly used for, the processor to temporarily store some information while they process. It's not like something that you store a movie in. You don't store a movie in a RAM. But even that has a humongous storage density. How much exactly? 32 million times increase. 32 million times increase in storage density within a period of 50 years. That's how much we have managed to enhance our capability to store information. Okay, now take a look at, that sounds like a lot. That sounds very good. Should be very optimistic. But take a look at the data growth over the same time period. Okay, let's do that. Storage revenue, let's get back to it later, but let's first look at the volume of data created, captured, copied, and consumed worldwide. And this is 2010, it's 2025. If I ask you what kind of graph can you fit here, what would you tell me? An exponent, right? It's an exponential growth. Anything that is exponentially growing is either extremely good news or extremely bad news, as you can imagine, right? So we are creating information exponentially. If you're wondering why, what are we doing wrong? And what happened here? Like 2010, all on a sudden there is an exponential growth. Can anybody, we have to blame ourselves. Think about all the digital tools that we're using. You have a Facebook profile, you upload a photo, and you keep uploading photos. There are billions of people over in the world. They're all uploading photos or posting something. Facebook has to store all of this information, and they have to have a data center for that. And then they have to have a backup data center. What if somebody hacks into that, right? And then they have to have a backup of the backup. Just imagine, right? Okay, so how often do you go and delete all of your past photos and just, okay, let me save some space? How often do you do that? No? Every once in a while, like if you visit, I don't know, Smoky Mountain, you take like 10 photos and upload all 10 of them. And millions of people are doing so. Not just Facebook, LinkedIn, Twitter. Just imagine the social media. Billions of people uploading trillions of articles and stuff. And they're all going to be there. And they will only increase in storage density in general. So that's one aspect. I mean, obviously, you don't have to close your Facebook to save the world at this point, because there are more critical situations like ChatGPT, for example. When you use ChatGPT, hey, write this essay for me, you think it's a harmless thing. It's not changing anything. But ChatGPT uses, I mean, I'm not going to quote the numbers now, but we'll get back to the numbers later on, unreasonable amount of storage and energy. And just Google, after today, you can just Google, ChatGPT already uses more energy than some countries use in an entire year, like Argentina, the Netherlands, and Sweden. Okay, there was a New York Times article that reported it. So just Google it and you'll find it. And most of this energy goes towards accessing the information stored. Like when you train these models, this training information will have to be stored somewhere. So you need data centers to store all this training information. And there are many AI systems. ChatGPT is just one example that everybody knows and uses. There are many others, of course. Everybody has their own AI system. Microsoft has it, Google has their own system, Apple has their own system. So everybody wants to have their own powerful AI. And the AI will only be as powerful as the data that it collects. Can you imagine that? There is a saying in the industry now, data is the new oil. Whoever has more data has more, I mean, it's like as if you have more oil that you can sell. Okay, so we have a humongous increase in data. Think about all these space missions that we are taking up, all those photos that we're taking. You spent hundreds of millions of dollars to send a space probe somewhere. And all the photos that it is taking, you're storing all of them. Will you delete? Oh, it doesn't look good. Just delete it. No, you spent 500 million to a couple of $1 billion just to create that thing and send it out. Whatever it sends you, you have to keep it, right? For the future generation. Maybe I'm not making anything out of it now. Maybe somebody else will figure out some trend. Let's keep collecting data. And you'll be surprised to know, even the older generation space probes that we sent out like 50 years ago, they're still sending us data and we are still storing them. NASA, not we, like NASA is still storing them. Okay, so a continuous source of data that you are storing and will keep storing. Okay, again, while we are on this topic, at the very end of this lecture, there is a slide where I want to go for a second and want to show you one example that you may not have thought about. This is CERN. How many of you have heard about CERN? It's good, many of you. Practically the biggest ever experiment that human being ever took up, and arguably the most challenging engineering feat that ever took place. It is so big of a laboratory that it covers multiple European countries. So the thing is, CERN creates humongous amount of data. Notice in 2010, it used to create 18 petabyte of data. Now it creates 1,000 petabyte of data. So now it is basically in the exabyte level. So every time it runs an experiment, and I wrote it here, just read it. Up to about 1 billion particle collisions can take place every second. By the way, I forgot to mention what they do. They take particles and collide them and break them down and try to study and find new particles, new fundamental particles, okay? So like hardcore physics, sure? But as the number says, every collision will create 100 billion particles and you have to track all of them and track their movement so that you can identify whether this is a new particle or an old one. So just imagine during every experiment, you create a humongous amount of data that you hardly can store. And that's exactly what they say. We cannot save everything. So they use a trigger system, meaning, is it important? Is it exciting? Then let's store it. Is it not? Then just discard the data. So CERN basically has to discard most of its data because it doesn't have enough storage. So basically CERN partnered with the biggest memory maker in the US, Micron Technology, to create a data center. Like they cannot just buy stuff. Like they need so much storage that they cannot just buy, give me like 10,000 hard drives. No, that's not gonna work for them. They had to create dedicated storage system working with Micron memory maker in place. And we don't even probably consider that to be one of the biggest source. If nobody else buys it, if nobody else, like Apple doesn't buy storage for their iPads or iPhone, nobody else does it. CERN itself will be a viable customer for Micron for the longest time. You see that? Anyways, so, and these experiments are being done recently. They were not done in 1980s or 1990s. So we didn't need that much data. We are almost running out of time, but it's okay. Today's lecture is like more like hyping up the topic mostly. And by the way, if you don't care about really storing information, you should care about the money. Some people like industry folks do care about money. They run after the money. So that's where the storage revenue comes in. You see, the revenue is growing. I mean, I wouldn't say exponentially, but also pretty dramatically over year after year, you see? So as more revenue grows, more companies will come in the market to make money. Like, hey, let's make a memory making business, okay? Because there is ready customers. Nobody will ever, I don't think the demand will ever die down unless everyone in the world decides we're gonna shut down all of our digital data creation. We'll not take any photos anymore. We'll not create any audio anymore, not release any movie anymore, like nothing, literally. Unless that happens, it's very difficult to go back. Okay, these are all data. I want it to be data driven, right? Rather than just me telling you this is very important, just care about it. DRAM manufacturer revenue. I want you to pay attention to some names because most of these names are unknown. You have all heard about Samsung, I hope. How many of you heard about Micron before? Some of you, only a few, right? How many of you heard about the others? Probably not, right? You don't even see Intel in here, by the way. So memory is a very different business. There are some known players like Samsung, for example. SK Hynix is South Korean Hynix. It's another big player. And notice, this is Samsung's share. This is SK Hynix share. And this is Micron, which is the biggest memory maker in the US. So that's where US is. It's not even third, okay? Notice that. Yeah, they're growing, by the way. They're doing better now. This is old story. This is more recent. So Micron is growing. They're creating a new fab in New York. They have a fab in Idaho. They're going to grow, obviously. So Micron is big US giant, but there are other giants in the market in general. That's for DRAM. Flash, and I showed you, DRAM and flash are all that matters in today's market. Similarly, Samsung is basically the giant even now, but Micron is increasing, but there are other entities like SK Hynix and so many others who are also growing. And Intel has some minor share, you see that? And all of a sudden, they're not there anymore. I don't know if you're following what happening to Intel, but that explains. They basically sold their memory business to SK Hynix, literally. So anyways, the dynamics involves a lot of major players. So the people that I will be inviting to talk about memories, hopefully will give you more perspective. We just have 1 more minute left. We will not be able to finish today's lecture, but that's okay. The remaining few slides we'll just quickly finish up in the next lecture. And then we'll move over to the first technical lecture. This is not technical, it's more like a marketing lecture, honestly. But we'll move over to the next technical lecture in the next class, okay? All right, thank you. We'll start from here in this lecture, in the next lecture.